So, good morning, everybody, and welcome to the Flex-Rigid in the EDA-tool webinar. Today, we will continue the last webinar from April, where we cared for the Flex-Rigid standards from Würth Elektronik. And today, the agenda shows a short introduction into Flex-Rigid technology and the relevant topics for the EDA tool and the layer stack design. Then we will see the standards for the Flex-Rigid layer stack design on paper, let's say, and finally, number 3, the digital versions of these standard layer stacks. And last but not least, number 4, we will show you samples and give you a demonstration of a special layout. This will be performed by my colleague Jürgen Wolf. So the advantages of Flex-Rigid, we remember that there is a big chance for miniaturization using Flex-Rigid. The next thing is to improve signal integrity remarkably by using Flex-Rigid, get rid of all the solder joints and the transitions over cables and connectors. Third advantage is better reliability using this integrated Flex-Rigid solution. And the last chance is to use Flex-Rigid for dynamical bending if the design is done correctly. This is a slide from the April's webinar about the standards for Flex-Rigid, and today we will care for the highlighted, red highlighted points, stack-up plans, and from the stack-up plans, the standards, and for the variants 1F XRI, that means one flexible layer outside, and XRI 2F XRI, that means Flex-Rigid stack-ups with 2 copper layers on inner layer flexible core. The design flow for a Flex-Rigid design is starting, of course, with the mechanical design, and the next thing, of course, we need a wiring diagram and a component list. Then starting in the EDA tool with the layer stack up. And for this point, there are some special things to be considered. We have different areas, flexible area, rigid area, and of course, different stacks for these different areas. So the tool should have a multiple stack option to do this. For example, in Cadence, for this you need the professional version. That's not included in the basic version of the Cadence tools. You have to do the definitions for the materials and the layers. Of course, you will have flexible materials, you will have maybe flexible solder mask and polyimide cover layer for the flexible areas. And finally, you have to documentate this. On the right side of this slide, you can see some possibilities how to do this. And then point 4, you will have to run a board planning mode to learn the system where the flexible and the rigid areas should be. But before we will start to do the layer stack design, I will give you some hints which are very important. So Flex-Rigid is mechatronic system. That means you have also to consider the mechanical design. So all electrical and mechanical interfaces must be taken into consideration. And if you see a chance to optimize this mechanical construction, you should do that, as this could cut costs remarkably. On the right side, we are looking into a box and see a mechanical design with some components distributed by accident, let's say. And if you make a flat view of this construction, you will see that this needs a lot of area, so that this will be very expensive. And the solution below, if there is a chance to optimize this, to move the components and change the connection between the components by this flexible area, you will see that the flat projection of this is much smaller compared to the first original design. So this is important to consider. The next thing is that we often see long tails leaving the rigid area in different directions, thus preventing nesting in the delivery array. So it's important to optimize the needed area for the design, maybe combining interfaces and also considering the option of folding. Let's have a short look at an example from some years old. The round area is a rigid area and 3 flex tails leaving this rigid area, ending in another rigid area for connectors. So placing into our production panel, as the design is really big, that shows us that we have these red areas wasted, and so you have to pay for it, but you don't have any effect out of it. After a discussion with the engineer, they rethought the location of the interfaces and the design, and finally ending in this design, which could be placed 4 times in the same area. So this cuts costs dramatically, of course. And the next thing is to think about the option of folding, as you can see on the right top side, folding and then getting a straight flex, not needing a lot of area in the production panel. So on the left model, the green model with the components on it, you can see that there is the use of folding in different areas, thus getting a flat projection on the bottom side in black, which does not need a lot of area. To be honest, the flex tail on the top side, I would like to change this also, but that's the point for discussion to another optimization. Another important thing to consider is the stack-up itself, and there the question, how many flexible layers do you really need? So 6 layers, this is a 6-layer stack-up, but with only 1 copper layer in the flexible area. So if this is sufficient for your design, 1 copper layer in the flex area, this is very cost effective. This is also on the right side a 6-layer design, but this time with 2 flexible layers inside. And the comparison in terms of cost, if you assume that the left approach costs €1, the approach on the right side definitely is much more expensive, nearly a factor of 2 more expensive. So at that point, before you start with your EDA design, you should really ask about the necessity of several copper layers in the flex area. So this is a main cost driver. After all these checks, then we can start with the layer stack. The Flex-Rigid layer stack, we have a nomenclature for this, showing us the copper layers on the rigid part and the copper layers on the flexible part. Rigid with the abbreviation RI and F for flex. As you can see, here we have an 8-layer construction with 3 copper layers on rigid from top down, and then 2 copper layers on the flex symmetrically inside, and another 3 copper layers again on rigid material down to the bottom layer, followed by a number, in this case 1.6, showing us the total thickness in millimeters, again followed by the thickness of the base copper on the inner layers. So this is 18 micron copper on the inner layers. This is the standard. Of course, it's also possible to have 35 micron inside, but this is not the standard. The standard, as I already mentioned, 18 micron copper inside on the inner layers, on TG150 material, halogen free and with fillers. For the flex material, we are using adhesiveless polyimide, and for flex outside, as you can see here, we are using flexible solder mask only in the bending area as a standard. It's also possible to have cover lay in that area, but that's not the standard. And we can have 1 layer up to 8 layers in the standard using this box here. And for flex inside, the standard looks like this. Again, the same mid TG material, TG150, polyimide without adhesive. And in the flex area, we are using now polyimide cover lay, only partially in the bending area with a small overlap into the rigid area. So this is the standard and the tooling box for building 4, 6, and 8 layers flex rigid with inner layer flex. Now let's have a look at the digital standard layer stacks. Using the Altium tool, Altium Designer revision 18, using the layer stack manager, the thing is that we want to have an 3RI, 2F, 3RI. So I have loaded the preset 8 layer construction. And as this is a core lamination plan, I have to change the cores and the prepregs and adapt the thicknesses of copper and dielectric. That means core thickness and prepreg thickness. Next thing is in the window advanced, add another stack, which is then the flexible layer. And in this flexible layer, I have to deselect the not used layers in the substack flex. So all the rigid cores and solder mask and so on is deselected. So now we already can see a flexible area with the 2 cover layers. And then we have to add the cover layers for these areas, which is done by add layer, add flex cover layers. So this is some work to do, and of course there's the risk to make errors. So now there's a chance to make this, to have this much easier. We will show you afterwards. So we are already providing the standards showed here. Besides the first stack up, the 1FORI, this is a stack up with only 1 copper layer. It's not possible to do this in the EDA tools, as they always require a top and a bottom layer. So you have to use a 2-layer construction and not using the bottom layer, for example. So what is the status quo today? So we are providing all the variants you can see here as PDF, paper work, let's say, and for Altium and Cadence data format, we are already providing the 1F XRI versions standards and the XRI 2F XRI standards on the internet. And this is a point where I give over to Jürgen Wolf, who will show this in detail. So Jürgen, it's your turn.
So thank you, Andreas, and a warm welcome from my side as well. I hope you enjoyed it so far. I will show you where you will find our layer stacks on our website. So I opened our main window from our website, and directly in the middle you will find the point printed circuit boards. So we will go there. And on the left side on the menu you will find the point products. So we open products, and we have the Flex-Rigid section in this menu as well. And in this Flex-Rigid section you will find this point build-ups. And in the build-up point, you will find that there is the mentioned stack-ups in the PDF format. Then you will find already the stack-ups to be imported into ORCAD and Allegro, as well as the stack-ups which can be imported into Altium. And a more general format is the newly created IPC 2581 format. So this is already on our website in one or other version. We're not fully completed yet, so we are still working on it, but there are already some of those stack-ups which we already provide in PDF formats in several years, transferred into the different EDA-tool specific versions. Today, we want to show you how to proceed in Altium. So we go to the Altium section. And here you will find the stack-ups being provided. And as an example, I will just choose one. For example, let's go to 1 rigid, 2F1 rigid with a thickness of 1.55 millimeter. So when you click onto it, you are prompted a new window to download it. So you can download it and choose the right folder. In my case, I will use the webinar folder. So I downloaded it now. Then you can switch over to Altium, and I just opened a new PCB document. So this is the new PCB document. And when we look into the layer stack manager, which you will find in the bottom menu of the layers, you do a right click on any layer, and then you can choose layer stack manager. And as I said, I just created a new PCB document, and depending on if you already changed the standard template or whatever, this is the standard installation template. You will find a double layer stack up in the layer stack manager. So we want to change this by using our stack up from the website. So we go to the top left, there you will find the button load from file. You can go to your folder where you saved the stack up file, use it, and load it into Altium. Then you will get prompted to have a look on the layer stacks. So Altium is trying to merge the previous layer stack with the layer stack to be loaded. So if you have already some layout on different layer, it's trying to move those primitive from one layer to another, and you see the merging layers. In our case, since this is a new PCB, there is nothing to move. So we do not need to check this in detail. We can just click OK. And you see the new layer stack is being imported into Altium. You will find all the different materials we are using here, the prepregs, the cores, the copper layers, the dielectric, polyimide film in that case, which is between layer 2 and layer 3. So this is the standard layer stack. Additionally, when we open the advanced tab, you will find the different board stacks. So on the left side, we have the general board stack, which is for the rigid area, which includes all the materials needed for the rigid area. And on the top layer stack on the left side, you see if the materials in the overall stack are activated for this specific stack. So we see in the rigid area, we have activated the top overlay, the top solder, and all the 4 layers. When we switch over to the flexible layer stack, you will see that we just activated inner layer 2 and inner layer 3 with the polyimide. so that only those 2 layers can be used later in Altium for the routing. All the other layers and dielectrics are not activated, only the cover layers are activated as well. Additionally, when you go to the right side of this advanced tab, you see that the flexible stack-up, you need to activate that this is really a flexible stack-up. So you need to activate this button here. If you do not activate this button in the 3-dimensional mode, this layer stack will still be shown as a stack without all the other layers, but you are not able to bend it afterwards. We will come to this in the second demonstration. So there is a possibility to do real 3-dimensional bending in Altium, and we will show you how this is being done. So up so far, this is what I wanted to show you in Altium for the first section, and I will give back to Andreas.
So thank you very much, Jürgen. Always impressive how familiar you are with the tool. Now, point 4, samples. As you may already know, since years we are providing different variants in hardware samples. You can order on our internet presentation on our website, and the target is to show you the possibilities of Flex-Rigid technology and also to find out the differences between the different variants of Flex-Rigid and semi-flex and pure flex and flex with stiffener, flex inside or flex outside. So feeling and understanding, this is the target of our samples you still will get also in the future. But now at this point, we have created a new sample, which we call a digital exercise sample, and this is a cube, and this is to show you in one sample some different constructions and variants of Flex-Rigid, and we are proud to offer this also to you. So if you are interested in getting these data in the Altium 18 data format, so please drop us an email on our Flex hotline. You can see the link here, flex@w-online.de or .com. That's the same, more or less. And we will be proud to send you this data. So this is the point where I again hand over to Jürgen Wolf, who will show you in very detailed form how this is done in the Altium EDA tool.
Thank you, Andreas. And here you already see my Altium screen. And what I did is I prepared for this new digital sample the board outline. So normally when you look into your design and into your conception phase, you on some point have your mechanical department or your mechanical structure being done. And you either import your board shape into Altium by using, for example, a DXF file, or you create your board shape in Altium by using the mechanical layers. I've done this here directly in Altium, so I created on a mechanical layer this board shape and defined it already as a board shape, which you will find up in the point. Design rules, board shape, defined from selected objects. So what I draw on the mechanical layer, I selected everything and decided this should be my board shape. Based on this board shape, we can switch over into the board planning mode. So by typing number 1 on your keyboard, you can change to the board shape. And in the board shape, to make a Flex-Rigid design, you can define where is my rigid and where is my flexible area. To do this, I already created different layer stacks. So this is the setup for this sample, and this is a layer stack you probably will never find on our website, since all of the offered technologies are being used here to show it in one sample. So we have our rigid stack up. It's a 4-layer stack up with different materials in it. Additionally, based on this stack up, we have the 2F on the inner layers. So here we activated only the layer 2 and layer 3 copper layers plus the cover lay needed for the inner layers. Then we have an 1F built up on the bottom. So we have a polyimide layer on the bottom and the bottom copper layer plus a cover lay covering the copper on the bottom layer. Then we have a 1F built up, which is on the bottom layer as well and covered with a flexible solder mask. So in comparison to the other one, we have cover lay. Here we have flexible solder mask. And the fourth one is the so-called semi-flex, where we use a depth milling. And again, this is being shown here in Altium. So the depth milling is going from the back side, and we just activated the last prepreg and the top copper layer plus the top flexible solder mask. It is always important to have at least one full prepreg layer for the semi-flex bending area so that the glass inside this prepreg is not being damaged and the semi-flex can be bent well. Additionally, as I have just shown in the first section, all those 4 flex areas, we have the flex bottom activated on the right side. So we have for the 2F, for the both 1Fs, we have activated the flex. Plus, additionally, we have the semi-flex defined as a flex as well. Okay, so layer stack, everything is being fine. So let's go back to the board planning mode. In the board planning mode, now you have the option to define split lines. Split lines you will find in design, define split line. So from board edge to board edge, you can draw now a split line. The split line is used to define different areas in the board planning mode. So you've seen I've just created one split line and I've created 2 board areas now, the left side and the right side. And by double clicking into it, you can choose which layer stack is used for this area. So the layer stacks which have been defined in the layer stack manager can be chosen here. Additionally, you can define later for the build-up if cover lays are being used in this area and if this area is being locked in a 3-dimensional view. This is especially important because later on we can decide which is the base rigid area and which rigid areas can be bent. And I will switch the Altium document now. I've prepared this for the whole dice. So here you see I already created several rigid and flexible areas. For example, here, this is the rigid area. I called it 4 because the number 4 is on this rigid area from the dice, and I called it rigid. I have flexible areas here as well. For example, this one, this is a 2F, and I activated that there are cover lays on this 2F layer. Additionally, in the middle, this yellow line you see here, this is the so-called bending line. And if you double-click the bending line, or if you go to the left section into the layer stack regions, here all these different sections and areas are shown as well. You see the bending lines as well. So you can open such a bending line and you can define in which angle it will be bent. So in this case, it would be -90 degrees. You can define either the radius or the affected area width. So if you choose one, the other one is changed as well. So these are both basically the same. You only type in either the radius or the affected area. And the last point is the fold index. Fold index is important because here you decide when you have several flex areas and you want to check the bending, which one will be bent before the other. Or you can, if you give the same fold index, for example, you have 2 flexible areas and both give them the index 2. If during folding index 2 is online, both will be bent simultaneously. So based on this, I did this for all the areas of this dice. So when I change now to the routing area, And you see I just deactivated all kind of different layers. But if I activate all the different layers, you see I didn't add much tracks and space lines. I just added the dots for the dice and some additional information. And to see this better, I change into the 3-dimensional mode. So we switch, and you see the front layer basically just has the dots from the dice. And if we flip it, turn it around, you see on the back side we have the description of the different layers. And here you see very nicely that, for example, the 2F on the inner layer is being covered with coverlay. We have the difference for the two 1Fs. So 1F section is being covered with a coverlay, and 1F section is being covered with the flexible solder mask. What I forgot to mention is that in the layup stack-up manager, you can decide and define what is the so-called coverlay expansion. I just reopen it. So right on the back of this table, you see coverlay expansion. And here you can decide which amount or how many millimeters, in that case, because I changed everything to millimeter, how many millimeters the coverlay is being expanded, or the flexible solder mask, from the flex area into the rigid layer. So we have a part or an area where this overlaps, and this overlap area is being put here inside. So let's cancel this one. So we see this when we directly look in the 3-dimensional area. So this coverlay area expands into the rigid section. So let's try to rotate this a little bit so that you see when we directly go inside and have a look from the side, you see that Altium really is making this very nice. So looking, oh, sorry, a little bit too far. So when we look in detail, the inner layer 2F really comes from the inside of the layer stack, and the outer layer 1F is on the outside. So Altium is doing this very nicely, that you see directly how it's being shown in 3-dimensional view. And next thing, and I already mentioned this, is we can check in the 3-dimensional mode if folding is being done correct and if your mechanical design is done correctly. By changing again into the PCB tab, using the layer stack regions, all down to the bottom, you will find this fold state slider. And as I said, I created those flexible regions and I gave them fold indices. So by using the slider, we can now fold the whole setup. So you see each rigid part is being folded. And in the end, we have a so-called lock, sealing lock, or whatever you would try to call it. But you see that the cube or the dice is nicely folded. You can check if all the areas are in the right position as you want to have it. And for example, if everything is being folded in the right way, as you can see here, so this notch is on the right position and the lock is going inside as we want to have it. So this is what I wanted to show you in Altium, and as Andreas already said, we want to provide this Altium sheet and this Altium document with the layer stack and with all these areas already predefined later after this webinar, so that you can have a look on it. So thank you from my side, and I hand over to Andreas again.
Well, thank you very much, Jürgen. Very impressive. So let's come to the summary. As we know, we need really good standardization for Flex-Rigid. This is essential to meet quality and cost. And one part of this standardization is layer stack up. And for years, we have been providing layer stack up standards in terms of paper, let's say, as PDF files for downloading. And now these standards are becoming digital, as we have seen. And the implementation of these templates, as well for the stack ups, as well also for the design rules later on in your EDA tool will reduce errors and will improve your productivity. So that's a nice thing we will follow. The first standards we are already providing for Altium and Cadence. They will follow the standards, I think, also for Mentor and for Sugen tools. So this is more or less sure today. As well as more stack-ups will follow for the pure flexible stack-ups and also the 2-layer flex outside. In the next project step, we will care for the digital design rules and also implementing this in your tool, which will give a next kick for the whole thing. So let me give the last hint for this webinar. If you need more information about Flex-Rigid technology, you could find this in our webinar archive, and the next webinar in October, caring again for EDA tools, will show you how to apply the digital design rules, which we will create in the next weeks. So that it is for today, and let me say thank you for your attention, and we will come to the question section. And at that point, I also want to thank Jürgen Wolf very much for his support. Thank you, Jürgen.